Data have been around for a long, long time, but it was not until the middle of the 19th century when human beings got actively involved in analyzing the data. Statistics is a social science. It is a science that uses a great deal of mathematics. An ever-increasing number of universities and colleges have recognized the difference between mathematics and statistics and have created independent statistics department separate from the mathematics department. Some schools feel it is beneficial to retain statistics within the mathematics department. Quite frankly, the school at which I teach, Sam Houston State University, currently has statistics and mathematics as part of one department. In fact, our current department chair is a statistician. But that is neither here nor there, because we will be using a great deal of mathematics as we analyze data using statistical techniques. Statistics is the collection, display, and analysis of data. In this lecture, we are focusing on exploratory data analysis, EDA, of a single variable, of a single measurement. Data can be gathered from a single source or from various sources. In the latter case, the analysis will involve a comparison of the results from the different sources. For example, we could be looking at, for example, test scores from a particular school system, various schools within that system, or we could be looking at the same test scores from various school systems, and then, in the latter case, compare the school systems in terms of the average test scores or the distribution of the test scores. EDA is qualitative in nature. That is, we were simply looking at qualitative comparisons or qualitative analyses. We are concerned with measures of tendency, measures of variation, measures of pattern, and measures of extreme values. Once EDA is understood, one can work on what's called confirmatory data analysis or inferential statistics. This will be covered in lectures 22 and 23. But currently, in this lecture, we're going to look at exploratory data analysis. What we want to be able to do is look at graphical displays of data and numerical statistics that are used to describe data. And we'll see various applications of exploratory data analysis with different types of data. The effective analysis of data began in 1857. Although the analysis was disregarded and lives were lost because of the disregard for the analysis of that data, many British soldiers who would have lived died during the Crimean War because the data analysis that was done, and which was effective, was absolutely disregarded by those in charge of the British armies during the Crimean War. The importance of data increased throughout the latter part of that century. And we go back to that 1857 situation, and you ask, well, okay, why was the data not paid attention to? If the data was gathered from large numbers of British soldiers who were wounded and hospitalized, and the data was analyzed effectively, what could cause British generals to look at the data and disregard it and go on allowing hundreds, if not thousands, of their soldiers to die in hospital? Well, the answer is quite simple. The analyst, the statistician who gathered that data and analyzed that data was none other than Florence Nightingale. And Florence Nightingale, of course, was a woman. And the British generals living in the Victorian era did not regard the work of a woman as being scientifically correct, and therefore allowed hundreds, like I said, or thousands of soldiers to die. Her analysis, by the way, seemed to indicate that more casualties were dying from improper care and improper sanitation than from their wounds. In other words, they were not bleeding to death because the bullet had shattered organs and therefore there was no chance to save them. They were dying from diseases which they obtained while in the care of the doctors in the hospital. And again, despite the amount of data she had gathered, the professional manner in which she had presented her analysis, and the critical nature of her findings, her work was disregarded by the Army command, only because she was a woman. By the end of the 19th century, serious work was being done to bring scientific method to the display and the analysis of data. Carl Pearson heads the list of statisticians who helped formalize the making of decisions from data. In addition to his coin-flipping experiments mentioned in a previous lecture, Pearson invented the chi-square statistic, the oldest inferential statistics test that is still in use today. He also was a contributor to the study of correlation, a subject to be discussed in our next lecture. During the first half of the 20th century, Sir R.A. Fisher provided major contributions to the science of data analysis. He is given credit for inventing statistical experimental design and the formal methods to analyze data obtained from such experiments. During the latter half of the 20th century, John Tukey has been the guru of data analysis. He sought graphical displays which provided interocular impact. His words, interocular hits you between the eyes. Perhaps his most widely used creation is the box plot, or the box and whisker plot, a graphical display that we will examine shortly. There are many numerical statistics and graphical displays available to the statistician. We will look at a few of these useful examples, not all, because this is not a statistics course. A graphical display should allow the viewer to get some sense of pattern about the data distribution. Also, the nature of extreme values should be evident, and an estimate of a representative average, a typical number, should be apparent from the image of the data display. A sense of the amount of variation should be obtained by looking at that display. All of this is what we desire in a graphical display of data. A line plot is a simple and effective data display. Here is an example of a line plot. A number line is constructed and X marks are made above the number line to indicate the frequency of occurrence of the various values. Here we have values from 1 through 7. You'll notice there are 3 X's above the 1, meaning that 3 times a number 1 was obtained in our data collection. There was 1, 2, and quite a few 3s and 4s, and smaller numbers of 5s, 6, and only 1, 7. Again, this is just an example. Later on in the lecture, we will look at a specific set of data and see how the line plot allows us to examine the data and make some qualitative assessments about what the data is trying to tell us. By the way, some people's definition of statistics is torturing the data until they confess, and perhaps the line plot will give us an opportunity to do such a thing. By the way, some line plots you may see use dots rather than X's. It's the same idea. The fact is we are immediately looking at the plot to see the distribution. In fact, if we can go back to that graphical display, we'll see, for example, that most of the data is in the middle. That is, between 3 and 4, we have probably a good percentage of the data in this distribution. We can look at the shape of the data and say, well, if there were a few more 2s, we would have a mound or bell-shaped distribution. Obviously, there's probably insufficient data in this data set to make any strong analyses based on viewing the line plot. But the line plot does give us very excellent opportunities to identify things such as clusters, where the data are clustered together, or gaps between data, as well as potential outliers. Outliers are data that are far enough removed from the rest of the data to raise questions about why are they so far away. Again, the clusters and gaps are important because we asked the most important statistical question, why? Why are there no numbers between this and this? Why are there so many people or countries or cities that have this kind of numerical value and then another cluster over here? These are questions that are easily asked once one views an effective statistical display. A histogram allows the counts of data for various classes of data. Another example, another way to describe a histogram is a bar graph. where each bar represents a different class of data, and the height of the bar represents the frequency of data falling in that class. The histogram is an excellent device for assessing the pattern inherent in data distribution. Is the distribution fairly symmetric, or are the data skewed, that is, stretched in one direction? Let us take a look at a set of data with a histogram on the TI-83 to see what we can determine from this visual display. Here is a histogram of the ages at their inauguration of the various presidents of the United States. It is immediately apparent that this distribution is symmetric and that most of the presidents fall into two age classes. Each class, each bar, represents a spread of 5 years. Let's use the trace button on this calculator to tell us something about each of those bars. You'll notice that the first bar represents presidents who were age 40 up through but not including 45. And there were two presidents who were inaugurated in that age class. Those two presidents, of course, are John F. Kennedy and Theodore Roosevelt. If we continue down the graph, we have 6 presidents who were inaugurated in age 45 to 50, but not including 50, and then 12 presidents who were between 50 and 55, an additional 12 presidents who were between 55 and 60, 7 presidents who at inauguration were 60 to 65, and a total of 3 presidents who were past the age of 65 when they were inaugurated. You'll notice there are no presidents who are older than 70 at their inauguration date. So we have a very interesting picture of the distribution. We can see that there are no outliers. We can even take a guess at the typical age of a president is probably somewhere around 60 or so. We can notice the extreme values of in the 40s or in the late 60s, and very quickly we can analyze the data using this histogram. A second exceptionally useful graphical display of data is the aforementioned box plot, or box and whisker plot, that was designed by John Tukey. The box plot divides the data into 4 equal quarters. And from looking at the box plot, you can tell something about the average, the median, as well as 2 different measurements of variation. Let's go take a look at a box plot of real data to examine how this graphical display can allow us to look at data and make some interesting decisions. This is a box plot of the winning times in the Olympic men's marathon races from 1896 through 1984. As you can see, the box is divided into 4 sections. 2 are boxes and 2 are whiskers. Thus, the name box and whisker plot is sometimes used. The whisker on the left is the lowest quarter of the data. The same amount of data is in that quarter as in the other 3 quarters. That quarter extends from the minimum value to the lower quartile. The first box in the data is the second quartile, which goes from the lower quartile to the median. The median is the middle number of all the data. 50% of the winning times from those Olympic marathons were slower than that median, and 50% were faster. The third box, or the third quarter, which is the second box, goes from the median to the upper quartile, and again contains 25% of the data. And finally, the upper whisker is the fourth quartile, which goes from the upper quartile to the maximum value. You say, wait a second, what's that little plus sign doing out there? Well, that plus sign, you see, is an outlier. And therefore, we have an extreme value that is beyond what might be considered typical data for this distribution, and we identify it by separating it from the rest of the data. Now, the first question that might come to mind about the box plot is if those 4 sections, the 2 whiskers and the 2 boxes, each represent the same number of pieces of data, how come they're different sizes? The reason is it has to do with the variation, the spread of the data within each section. So in the second quartile, right here, That data is quite widely distributed, while the data in the third quartile, the other box, is much more consistent. Those numbers are much closer to each other. Again, the interesting question we can ask about these data is why? The most interesting why question based on that data set would be, why was there an outlier? Were the stopwatches not working that day? Did someone mess up? Perhaps all the good runners stayed home to boycott something. Well, actually, if I told you that the Olympics that had that outlier number was held in St. Louis, Missouri. If you've been in St. Louis in the middle of the summertime, you know that it's hot and it's humid, and that heat and humidity is not conducive for running 26 miles, 385 yards. All the runners participating in that Olympics ran slower than expected, and the winner had a time that was an outlier, much greater than the next largest running time. In fact, the next Olympics, 4 years later, the times went back to what was to be expected. But that graphical display immediately gives us the visual impact of the outlier, and we can ask questions such as why. Let us now look at numerical statistics that are used to tell us about data. The two most common measures of tendency are the mean and the median. The mean is obtained by adding up all the numbers in the data set and dividing by the number of numbers in that data set. You'll notice that the symbol for mean is X bar, and the symbol for summation is a Greek capital sigma. So we have X bar, the mean, is equal to the sum of all X, all the measurements, divided by N. N is the number of measurements in that set of data. The median is the measurement in the middle of a set. Now, whether you have a single number in the middle of a set of data is determined by the number of items of data. If, as in the first set of data, you have an odd number of items, perhaps have 5, and you put the numbers in order, there is a single number, 19 in this case, that is in the middle. So half the data are less than 19, half the data are greater than 19, 19 is the median. In the second set of numbers, we now have an even number of numbers, and there are 2 numbers in the middle, 19 and 20. So we actually split the difference, and the median for that set of data is 19.5. You'll notice that there are 3 numbers below 19.5 and 3 numbers greater than 19.5. Thus, 19.5 is the median, or the 50th percentile. The mode, or the value that occurs the most, is sometimes used to represent the tendency of data. It is generally used with non-numerical data. For example, if I wanted to know the average color that people want for a car, if I went out and took a survey and everybody told me their favorite car color, and I added up the numbers and divided by N, green 0.3 or blue 0.72 would not help. And in fact, I couldn't add those numbers up in any meaningful way. But if I said that the mode of those data was blue, then I would know that most people, or at least more people, chose blue than any other number. That was a typical number. But in numerical data, the mode is not as useful generally as the mean or the median. There are also measures to measure variation, that is the inconsistency, the spread of the data. The quartiles are at the 25th and 75th percentile. We saw those on the box plot, and we will look at those again. The lower quartile is the midpoint of all the data below the median, and the upper quartile is the midpoint or median of all the data below the median. Now, the difference between the two quartiles, the difference between the upper quartile and the lower quartile, is called the interquartile range, the IQR. It is a measurement of variation that shows the spread of the middle 50% of the data. It is unaffected by extreme values. The range is the difference between the minimum and maximum data values. It is a measure of variation and is totally affected by the extreme values. Let us go back to our box plot of the Olympic marathon winning times and take a look at the IQR and the range on that data display. Here is that box plot. You'll notice the range is from the minimum value to the maximum value. The question is, are we going to use that maximum, or shall we use the outlier as a maximum? Well, either way, you'll get a range, and the numerical value will be different, because if you use the outlier as your maximum value, you will have a much greater range. But you'll notice that the range is totally affected by the extreme values. The interquartile range is the distance from the lower quartile to the upper quartile, and it is totally unaffected by extremes. Whether you use the outlier or not, the interquartile range is the same. A third measure of variation is the standard deviation. This measurement is somewhat affected by extreme values, and turns out that it's probably the best of the three measurements. We don't want a measurement of variation that is totally determined by extreme values, but on the other hand, we do want the extreme values to have an influence, shall we say, on this measurement of variation. So the standard deviation, which is usually obtained from a calculator or a computer, is probably the most useful of the measurements of variation. The standard deviation, you will recall, was used when we dealt with the normal distribution. We talked about the standard deviation of the population sigma. A measurement of outliers. How do they determine outliers? Well, Tukey, John Tukey from Princeton, was the man who formalized the identification of outliers by declaring that any data value that exceeded the upper quartile plus 1.5 times the interquartile range was an outlier at the upper end. And any data value that was less than the lower quartile minus 1.5 times the interquartile range was an outlier at the lower end. I was present when Dr. Tukey gave a talk, and he was asked quite pointedly why 1.5 was chosen for this formula. We expected, that is, that the audience expected Dr. Tukey to say something like, well, the normal distribution, and come up with a bunch of numerical reasons. But he was much simpler than that. What he said was 2 was too big a number, and 1 was too small a number, and 1.5 was just right. And the world respects his choice, because today 1.5 is what it's used. Now that we have an idea about using graphical displays in numerical statistics, let's take a look at some more real data to see how we can analyze those data using graphical displays and/or numerical statistics. We are going to take a look at a data display of data from the 1984 Winter Olympics. The Olympics had numerous countries, and some of them actually won gold medals. We're going to look at a line plot of the countries and the number of medals each country won. What do you immediately notice about this line plot? Well, the first thing you see are there are two values all by themselves way far away from the rest of the data. You'll also notice that the data typically is skewed, and as you go away from 0, you'll see that the number of countries falls off. Well, who are those two countries out there beyond 20, way away from all the other countries? If I told you, and this was 1984, those two countries were the Soviet Union and East Germany, you shouldn't be surprised, because we know that countries within the Soviet bloc always tried to use sports to win the Cold War. It didn't work, and that is a pun because these were the Winter Olympics. But the fact is, it's immediately apparent from the line plot that there's something different about those two countries. Those two countries were willing to expend the effort and in many cases use possibly harmful drugs that endangered the athletes simply to win medals and get credence for their method of government. Now let's take a look at the graphing calculator and take a look at some data on Jimmy Carter and the election of 1980. So to the TI-83 we go. Here is a histogram of the percentage of the votes obtained by President Carter in the 1980 presidential election by state, you'll immediately notice this histogram looks quite a bit different than the histogram we looked at previously. It's not quite as mound shape, and the shape, in fact, is quite irregular. It's not symmetric at all. But the interesting thing about this histogram is to note the values. If we simply use the trace button here, we can see that our first bar, which is 1 high, there was one state that actually gave President Carter less than 25% of the vote. And if we continue up the chart until we get to the other bars that are not very high, there was one state that gave President Carter between 50 and 55% of the vote, and there was one state that gave President Carter more than 55% of the vote. In other words, of all the states in the United States in 1980, President Carter, the incumbent, received a majority of the votes in only 2 states. Again, the box plot could be used by political scientists to analyze that election and to talk about why President Carter lost. The first interesting question that one might ask is which states were the 2 states that gave majority votes to President Carter? Another interesting question, of course, was what was that state that had such a low percentage for President Carter? But I think the most interesting question from my political interest is what do you think the histogram for the winner of that election, Ronald Reagan, would be? Do you think he would have 48 states that had a majority of their votes for the Republican candidate? Well, it would make sense because if Carter only got 2, then Reagan must have got majorities in 48 states. Well, not quite, because this is an interesting situation. 1980 was one of those rare presidential races where there was a meaningful third-party candidate. And that third-party candidate, John Anderson, obtained significant percentage of the votes. So if you looked at a histogram of Reagan's percentages, you would probably find more states with majority, but not necessarily as many states as you might think if you didn't consider the influence of the people who voted for Anderson. In any case, from a political point of view, a simple histogram is quite useful in allowing us to ask questions and make analyses of a presidential election and the results from that election. Let's take a look at something involving consumerism. We're going to look at some data about hot dogs. Now, hot dogs obviously are a very American treat, and people eat hot dogs all the time. And there are typically 3 types of hot dogs. There are beef hot dogs, there are meat hot dogs, that is, hot dogs contain both meat, that is, both beef and pork and their byproducts, and poultry hot dogs where the meat is from turkey and or chicken. And the question might be asked, if I'm concerned about counting calories, which hot dog, which type of hot dog, beef, meat, or poultry, is in my best interest? Is there a significant difference in the caloric content of the 3 types of hot dogs? A comparative box plot will allow us to do this. So let's go back to the TI-83 graphing calculator and look at 3 box plots, one representing each of the 3 types of hot dogs. The box plot at the top of the display is for beef hot dogs. The second box plot is for the meat hot dogs, and the third box plot is for the poultry hot dogs. The first thing that you will notice is that there is very little, if any, difference between the medians for beef and for meat hot dogs. Remember, these data are on the caloric content of a serving of each of these various brands of hot dogs. But the poultry hot dogs median is significantly lower. But of course, how much lower is it? We don't have a scale. Using the trace button, we can see that the median for the beef hot dogs is 152.5 calories. For the meat hot dogs, 153, not much of a difference. But for the poultry hot dogs, a measly 129 calories. So therefore, one can say on average, poultry hot dogs are lower in calories. We also can look and see that the variation between the various types is not significantly different. EDA techniques can be used to compare sets of data, to explore patterns in the data, and to look for changes in those patterns over time. These techniques can be used to make estimates about the population based on data collected from representative samples. The examples involving Olympic data, presidential election data, and hot dog data demonstrate how useful these EDA techniques can be. In the next lecture, Lecture 21, we will look at the analysis of two-variable data, and in Lectures 22 and 23, we will get involved in quantitative data analysis.